Cambridge technology, and the project that we've been working with is stepper motor motion control for scan system. A scan system is a product developed by Cambridge Technology that combines both hardware and software to deliver laser beam steering solutions. The video you're seeing on screen provides a good demonstration of just what exactly that means and what this product does. So here you see a physical scan head apparatus that takes in a laser beam and then steers it onto a plane to etch or drill a user-defined design or pattern. Inherently, you kind of see the limitation here. That's with a fixed scan head, we've kind of induced a fixed area in which a user can design. And this is the core of the problem that we're trying to attack with this project. And of course, you could move this target plane, but that's more of an ad hoc band-aid than it is a real solution like we're proposing here. So with this fixed static scanning area, by introducing stepper motors to actually guide the physical scan head apparatus, we now create a dynamic, resizable range that users can etch their designs into. And this surely increases the applicability of Cambridge Technology's product and allowing for more complex, deeper, and larger designs. So the best anticipated outcome for this project then is threefold. At the lowest layer, we need to provide hardware that's optimized for reliable and uninterrupted pulse delivery. And then a bit further up the stack, we need to design we need to design firmware that's capable of accurate and precise motion profiling and trajectory profiling that takes into account things like acceleration, velocity, and smooth starting and stopping. And finally, we need to integrate our final project into their final product, and that is the full scan system. So the block diagram that we've designed for this project is one that we've really configured for development and made it easy to develop in, and that's because this hardware platform that their proprietary technology sits on top of is one of the most complex and complicated in the industry. And that is the Xilinx Zynq dual-core ARM Cortex-A9 plus FPGA fabric processor system. It's a beast, it really is. And it uses the full stack of Xilinx tools for software development, hardware development, as well as multiple channels for programming, serial analyzing, logic analyzing, and pedalinks for debugging. But mainly the outputs of this system are meant to port directly to a microstep-enabled motor and motor driver that plug directly into a linear slide that will actually guide the physical scan head, increasing this allowing for this resizable scanning region. But what is most important here is that we're developing an environment that's as close to the final application space as possible. And in a sense, we're developing an environment that's ready for deployment, which will allow for easy testing and testing that is accurate to the end use case.
So our first step in creating a system from which we can control our stepper motor was creating a space in the hardware logic from which we can take in inputs from the board, like clock signals and reset signals, and then sending out our own outputs, namely the step function and the direction function, to the external ports on the board. Now, this was no easy task, as we were working in a design environment that we'd never used before, Vivado, and we were coding in a language that we had never used before as well, Verilog. The main difficulty in this was that our design system was fighting against us, where every time we tried to create a logic signal, it would optimize it out and ground it. We eventually found a obscure command called don't touch that forced Verilog from messing with our system, and now that we had an area from which we could create signals, we had to figure out what kind of signals we needed. This was done by testing with a function generator from which we could experiment with different amplitudes and frequencies to see what we needed to drive the linear slide at a operating speed and pace that was good and smooth. This was then also used to test the different step settings, so steps per revolution, where a higher number of steps would create smoother and more accurate movement, but however it would be slower. So once we decided on a configuration that we liked, we put it onto our motion control, on our SMC. This was a difficult task, and we eventually got it to work, and you will see our setup in the next slide. So here you see we have our logic fully parameterized so that the user can simply set the distance, and in this demo application we have it oscillating back and forth, and you can see that we have it set to 4 inches, so it'll move back and forth at a 4-inch period, and then you will see that we double the distance, which then increases the range over which it moves. This is a good first step in a full motion control system that we will need for our best anticipated outcome. You will also notice that we can change the point of origin from which the stepper motor oscillates.
So finally, from a firmware software perspective, we need to port our existing underlying mathematics from mapping calls to move distance to pulse domain or time domain pulse sequences. We need to port that up into the firmware layer where users will be able to, or programmers and users will be able to interface with it through a robust enough API. And this is really what you're seeing as the first steps of that. Communications between the bare metal core of the dual core system and the actual FPGA fabric is quite complicated. The manual for how to do so is several hundred pages in itself. So we had to take a real concise and targeted approach to figuring out how we might be able to actually load and customize firmware scripts on the bare metal core. So we wrote a simple test script just to make sure we understood the flow of how to do this, in which we would just write hello world to the serial output and then read it back using a debugging tool. And as you can see here, we were able to be successful in that task. So this really lays the foundation for the rest of the project in integrating high-level control in an API that's robust enough to handle the industry's most complicated and user-intensive tasks. So for remaining technical challenges, we need to develop more mature motion profiling mathematics that will take into account things like acceleration, smooth starting and stopping, and velocity profiles, as well as implement this high-level control in a robust API. And then finally, we need to integrate it into the full SMC architecture, into their full final design. And then demonstrate that this API is in fact robust enough and is in fact useful enough to be used in the industry's most complicated tasks that there are. Finally, we'd just like to thank everyone who supported us throughout the process, and we look forward to continue to work hard on this project.